Hey everyone, we are back for Advent of Code in Ruby, Day 8, keeping the trend going, strong, daily streams every day, doing Advent of Code because otherwise I will likely become incredibly unmotivated and not finish it up. Turn down the music a bit, that looked like it was getting pretty high in the monitor there. So, we've already talked about what this is 7 other times, so we're just going to get into this, okay? So far, we are trying to go on vacation instead of saving Christmas for a change, because everyone needs a vacation, especially in 2020, good lord. So let's get into what is today's problem. Day 8. Handheld halting. Your flight to the major airline hub reaches cruising altitude without incident. While you can start checking the in-flight menu for one of those drinks that come with a little umbrella, you are interrupted by the kid sitting next to you. Their handheld game console won't turn on. They ask if you can take a look. You narrow the problem down to a strange infinite loop in the boot code of the device. You should be able to fix it, but first you need to be able to run the code in isolation. The boot code is represented as a text file with one instruction per line of text. Each instruction consists of an operation, ACC, jump, or no op, and an argument, a signed number like +4 or -20. ACC is the accumulator. It increases a single variable, global variable called accumulator. So you can +7 to increase it by 7. It starts at 0 after an ACC instruction. The instruction immediately below it is executed next. That all makes sense. Jump. Jump jumps to a new instruction relative to itself. The next instruction to execute is found using the argument as an offset from jump instruction. For example, jump +2 would skip the next instruction. Jump 1 would continue to the instruction immediately. Okay, so jump doesn't implicitly move to the next. ACC actually kind of like implicitly has a jump 1 in it also. That makes sense. And jump -20 would cause the instruction 20 lines above to be executed next. No op stands for no operation. It does nothing. The instruction immediately below it is executed next. Okay, and they give us some example input. These instructions are visited in this order, so we start off with no op, that does nothing. ACC plus 1, that means our global variable becomes 1. Jump 4, so 1, 2, 3, 4, we end up here, ACC plus 1, and then we go jump minus 4. 1, 2, 3, 4, we get ACC plus 3. I'm not keeping track of like what the counter is at. Jump minus 3, 1, 2, 3, ACC plus 1, so we just go to the next one, and then we're back at jump plus 4. So we are a solid jump plus 4, so now we've hit a loop. Yeah. That's interesting how they have it on the chart. This actually looks a little confusing to look at. But maybe that's a good structure for this. I don't know. First, okay, so they talk through what we just did by hand there. This is an infinite loop with this sequence of jumps. The program will run forever. The moment the program tries to run any instruction a second time, you will know it will never terminate. Immediately before the program would run and can run an instruction a second time, the value of the accumulator is 5. Okay, that's totally fair. Run your copy of the boot code immediately before any instruction is executed a second time. What is the value of the accumulator? So let's start off. We're gonna make a new directory here. Day 08, cd day 08. And let's copy over day 7's problem 1. God. Up one directory. Day 7, problem 1. We're just going to copy that here because we'll just borrow some of the boilerplate. Because once again, we're going to be reading lines from a file. We're going to be chopping off the end, so we can just keep what we have there for that. Okay, and let's make a input sample that we are going to use to just get this started. We're going to use the example they gave us, just so we can kind of have some testing and proof of concept and confidence that our code is working. Don't need that file anymore. We do need this file though. 100%, that's our new thing. Okay, so a lot of this can go away. All we actually care about, oh god, a lot of this we can get rid of. We don't need any of this tomfoolery. We're not doing any searching. We're just going to hold on to input lines because and our main function here. And as we have been doing, we're going to just switch this over to sample text initially so we can test this out. Okay, so we're basically parsing some rudimentary assembler here. So that's actually not too bad because the structure of assembler is basically you have some sort of instruction, you have a space, and then you have a numeric thing. Let me actually test one thing out real quick. I think this actually works. Okay, so we can split on space, and then we can just cast the second half of it to integer. Okay, so let's just take our input lines, and we're going to turn it into a structure here. We're going to turn it into an array of 2-element arrays that are going to have the type of instruction and what it should be doing. Put lines, each do line, and we're just going to do line split on space. We're going to end up with instruction. What do we call this? Maybe just value. That's not a great number. Instruction int. I'm not crazy about that either. And then we can just return this. because we're actually going to want to iterate through this. We're not just going to do, let's actually make this a map. So we're casting that to integer. So now we have our instructions. I'm trying to think. We don't actually want to kind of like just do this as a loop, right? We actually kind of just want to like not as like a for each or even like a for a linear like a for I plus plus sort of loop, right? We're gonna do something a little different here. I think we just kind of like want an infinite loop, and then we're gonna break out when we see the same instruction more than once, right? That's the idea here. Okay, so let's take a memo, scene instructions, and we can just have the indexes here for that. We'll just record these indexes as we go along. And we can set, let's start this off so the current index will start off at 1. Let's actually be a little less verbose here. IDX. While we can actually do until. Ruby has a lot of languages they have if and a while. Ruby also has until and unless. Some people like them, some people don't, but I think it works well here. Let me turn this up a little bit. There we go. I'm not just talking into the emptiness here. Scene instructions includes. Oh, every time I forget which one this is, right? ABC include cloud include. Can we include include A? Okay, so it's actually include. Okay, so initially this is always going to be true because scene instructions has nothing in it. And what we will be doing each time is we're going to be adding that to our list there. Oh, and we also need an accumulator. And that starts off at 0 as well. Okay, so next thing we need to do, we have our instructions in play. Actually, before we go any further, let's actually just have a little paranoia here. We're gonna pre-print our instructions and return early, just to make sure that this is... there's no reason to believe that we didn't parse the structure properly, but I just like being paranoid and running frequently. It's the TDD in me. Okay, so we have no op 0, ACC 1, jump 4, ACC 3, jump minus 3, ACC minus 99, ACC 1, yep, jump minus 4, ACC 6. Okay, so we know that we're parsing everything right, so we don't need to worry about that part. Let's clear that out. Okay, so we are making note of where we are. So it seems like there's two very different paths that we can take here. There's 3 different codes that we have to work with. So, and 2 of them automatically increment the index, and 1 of them doesn't. So let's... I actually don't think it actually makes sense to group those together. So, now that I'm thinking about it. So if IDX equals noop or nop, they're all 3-letter things. Oh man, let's hope that doesn't screw me up again. Last time I had 3-letter things, I accidentally had the word blue instead of BLU, and we took an extra 40 minutes or so tracking that bug down. That was that was not a fun time for anyone. Quite tedious. Okay, so we have NOP, and in that case, we just increment. Do we need to, like, maybe, make sure we're not, like, overflowing as well? We can actually be a little more... We're just gonna turn this into, like, a straight-up forever while loop. And then have explicit breaks here. I think that's a little easier to read. Is it greater than or equal to? I think that they're always going to give us input that's going to have an infinite loop, so the second condition probably doesn't even matter. But I like being a little more paranoid. And let me make sure I'm not being dumb here. I feel like I'm making off by 1 errors. So if we have that, and then if we do 3. So we don't want it to be equal, because equal will already be an overflow. Okay, cool. Let's move on. Let's move on. Else if IDX, what are the other options? Because no-op does nothing else. ACC, index plus equals 1. And we're going to have plus equals whatever... You know what? I'm actually being really dumb here. We actually need to do something else first. Instruction int. Because we're not... The index is just a number, right? That's not the actual instruction. So we want instructions at IDX. That's actually what we want here. Perfect. So now we just do instruction nop instruction ac. So we also need to add on the int onto here. If this is negative, it will add a negative, so it'll work the way we expect it to. Else if instruction equals, what's the last one? Jump. Okay. So jump, we're not going to have the index plus equals 1. What we're going to do instead is plus equals int. And we'll just do else invalid opcode. I don't think they're going to throw any invalid opcodes. They've been pretty good about having clean input for us. Let's just run this against our sample input and see what pops out the other side. I didn't print anything out, so nothing's going to print out the other side. Okay, so let's put the accumulator, because that's what we ultimately want here. What? Why would it do this to us? Very embarrassing. Okay, let's break if... Okay, so let's... Let's see what this is doing. Oh, I don't know what that was. Scene instructions include IDX. Do I need that logic reversed? No, we don't. 16. Instruction size. What? IDX is greater than that? Oh, no, no, I want this to be greater than instruction size. Okay, we just used the wrong variable there. That makes total sense. So it's going to break out. We'll take out our binding pry for now, and now it should work perfectly. Fingers crossed. Okay, let's run this again. 5. Okay, that's what we were expecting there. Perfect, okay. So now let's download our puzzle input. Give us that puzzle input. Yes, we do want that in there. Okay, so we have our input. That looks like how it should, right? Okay, let's just switch up our file, and we'll be. No, we're not doing that. No. We're still in part 1. Why am I thinking that we need to switch the file up? 1553. Okay. Okay. Well, I guess at this point we just have to trust ourselves to fate and hope that we don't get the timeout of shame. Because honestly, with this one, I don't really know what I could have possibly done wrong here. Our tests worked properly, so it'll be really embarrassing if I hit submit and we don't get a star. So here comes a star, and we have a star. Perfect. Let's see what we got in part 2. After some careful analysis, you believe that exactly one instruction is corrupted. Somewhere in the program, either a jump is supposed to be a NOP or a NOP is supposed to be a jump. No ACC instructions were harmed in the corruption of this boot code. The program is supposed to terminate by attempting to execute an instruction immediately after the last instruction in the file. By changing exactly one jump or NOP, you can repair the boot code and make it terminate correctly. For example, consider the same program for above. If you change the first instruction from NOP to jump, it would create a single instruction infinite loop, never leaving that instruction. Okay. If you change almost any of the jump instructions, the program will still eventually find another jump instruction and loop infinitely. However, if you change the second to last instruction from jump -4 to NOP -4, the program terminates. The instructions are visited in this order. After the last instruction, ACC +6, the program terminates by attempting to run the instruction below the last instruction of the file. With this change, after the program terminates, an accumulator contains a value of 8. Is this the same example from before? Let's open up, I want to see if we need to change our sample input. NOP 0, ACC 1, jump 4, ACC 3, jump -3, ACC -99, ACC +1, jump -4, ACC +6. Okay. If you change the first instruction from NOP to jump, yeah, so that would always be an infinite loop. If you change almost any of the jump instructions, the program will still eventually find another jump instruction and loop forever. However, if you change the second to last instruction, this guy here, the program terminates. The instructions are visited in this order. After the last instruction, the program terminates by attempting to run the instruction below the last instruction of the file. Okay. Fix the program so that it terminates normally by changing exactly one jump to NOP or NOP to jump. What is the value after the program terminates? Interesting. We'll look at our input for a second. So if we get to jump +1, we're really happy. If we get to this line here. If we get anywhere like over here, we're really happy. I'm trying to think, how would I pragmatically do this? That's really interesting. I mean, hypothetically, we could. It's only 300 some line, or no, 500 lines. Still fine. We could try brute forcing. There has to be a better solution than that, though. That doesn't sound like a good solution. I'm just going to think for a minute. We do have the... We do... Let's copy this over while I remember. We do calculate when we reach this point, so that's good, at least. We can initially change the win condition here. So we at least have notification of that part. Oh yeah, and we also still need to break. Or else we're stuck in there forever, and it's very sad for everyone. Just seems like there's a lot of... Brute force sounds like really bad. Rep input text. No, it's the other way. $58 of those. $238 of that. I guess if like no better idea is coming to me, I could try brooding this, I guess. The alternative, I guess, is because we do detect when a loop happens. We do detect when a loop happens, so we... So we could roll it back, I guess. That sounds really complicated, though. It's kind of like want to look at the input for a little bit. That's all benign. I think I want to look at what the scene instructions are on just like a vanilla run of this. And see what that looks like. Because the scene instructions will be in order, so I kind of want to get insight into how it jumps around. Ruby. Problem O2. And we go. What's happening at 335? 325 rather. You know what, how about what we do is we're gonna focus on jump, right? And we're gonna give ourselves like one get out of jail free card. So what we're gonna do is we're gonna see if jump takes us to a place we don't want to be. And we'll see if that gets us out of the loop. And so we'll kind of like detective, like, oh, I'm actually thinking maybe getting a little more complicated here. Okay. No, we don't actually need some over time because we'll be going back to instructions we've already seen. Okay, so we're going to mark that we haven't changed an instruction yet. So I think we can keep most of this, maybe, if I'm thinking of it correctly. Okay, this is this is pretty wonk. So let's break these out into. So what we're gonna do is we're gonna keep on going forward until we hit a loop, and then we're gonna back up to the last jump and change that. This has to be the last one, right? Oh, I don't know if I like this at all. I don't know if I like this at all. No, no, no. It is better than brute force, though. Oh boy, I'm thinking through how I want to do this here. I think I might want to refactor this out a little bit so that this is all actually a method, because I think we're going to be calling this a few times. Let's actually back this out a little bit. Let's just call this run program, because that's what we're doing, right? And I think we're going to be adding, and we're not doing this yet, but I think that we add an attribute that's going to specify which one we skip. So we're going to need. Okay, so we're passing in the program. Everything else I think is self-contained. We can just grab this. We grab all this. And we return accumulator. Perfect. Okay. And then we just right now well let's just print out what we have so far. This should be the same value as we had before. Okay, so oh, we changed the name to program, so that's not perfect. That's not great. We'll just keep the name here. I actually like the name program a little bit better, but that's fine. I don't want to have to change that everywhere right now, so let's just do that. Okay, 1553, so that's consistent. Oh, brute force is actually so easy now. So we're gonna add flip instruction. There's just no ups and jumps that we care about. And we'll make this initially -1. So this run should be the same. So it'll never hit. Flip instruction equals IDX, because we want this before any changes happen. IDX plus equals int else IDX plus 1. And then for jump, we do the same thing. Plus equal 1 else. So we're just gonna try everything, right? That's like actually like so insanely easy. So horribly inefficient, but so easy. And so instead of putzing, we're actually gonna raise. We're gonna raise an exception so that it just breaks out of everything, because this is so cringe. This is actually like the most cringe ever. So we're let's just run, and it should be the same because we're okay. So our flip is -1, so that's not an issue. With index. Line IDX. I think that's the order. Just testing out how with index works here. Okay, so it's so in Ruby, if you have an enumerable, any sort of enumerable, you can throw on with index instead of passing a block to it, and it will behave the same way, except it'll also have an index on there, and it's really cool. It'll add an index as like the next argument. So what we're gonna do is, oh my god, this is cancer right here. Cancerously cringe. Each with index do line. We're not doing anything with the instruction. We just want the index. I guess we could actually do 0 up to index collection size -1, but I think this is a little easier to read. So what we're doing here is we're just taking all the indexes for the instructions, and we're gonna say, hey, let's try flipping each one and see if that does anything. And it's not gonna do anything special if it's not a jump or whatever. It's not a jump or a no op, because those are the only ones we flip. But now we have special logic in there that will flip those in that scenario. This is really, really ugly. Don't ever write code like this. This is, oof. Especially this, because it doesn't actually run. Oh, no, because we actually we exit with an exception. Okay, so we found a scenario where we change one line and we successfully exit the program. We know that because we check when the index is greater than instructions size. I wonder if it's possible to jump like past it. That could actually be like an error condition. But if that happens, that would be like an error anyway, right? Anyway, we're gonna see if this just works. Oh my god, I can't believe I'm actually doing this solution. This is actually like a terrible solution for this. And we got the right answer. We were rewarded for our terrible brute force solution. I think all we do here is we just commit this all. Oh, I didn't commit yesterday. Also, let's oh no, because okay. At day 7. It's not showing me the folder names, so it's a little hard to see what's which. Day 7. And now day 8. Oh god, I hope that no one who's serious ever actually sees this code, because this was actually a terrible solution. And we're pushing this out into the wild, so no shame, no gain. We just have it out in the wild, and you know what? Say what you will. It was a messy solution, but we got done all in, including describing my thoughts, talking out loud, all throughout this, in under 45 minutes. We haven't been that quick since like day 1, okay? So I think we bow out at this point, and I say thank you. Please check out the Twitter and the Discord and everything else that's linked below. That'll give you notifications when we're back on. Drop us a follow. Do all the stuff that they tell you to do. Just do it. Just do it. It's gonna be fun. It's gonna be fun. We have chill streams for the entire month of December until we hit Christmas. I guess not the entire month of December. The entire month of December until Christmas. We will be doing these daily code challenges, and it's gonna be a lot of fun for me. I don't know if it's gonna be fun for you. I hope it's fun for you. But anyway, it's over. It's done. I hope you guys all have a great, relaxing